First of all, I want to thank the organizers in Barbara for this workshop on infinite dimensional geometry. Unfortunately, I'm going to talk about finite dimensional geometry this morning. I'm very sorry. So it's going to talk about differentiable structures on correlation matrices and application in neuroimaging. So a good start is to define what's a covariance matrix. So given a random vector, a covariance matrix is simply taking the expected value of xi, xj, minus the product of the expected value. So if you translate this into some matrix operation, it is simply the same as taking x and multiplying it by x transpose. So it gives me this notion of covariance matrix, which is simply an SPD matrix. Now, how do I build the correlation out of the covariance matrix? Well, I'm simply multiplying left and right my covariance matrix by minus a half of its diagonal, which is simply dividing by the product of the variances. Okay, so the space of all covariance matrices and correlation matrices are smooth manifolds and are denoted S plus and corpus in this talk, respectively. Okay. So we would like to put some way to measure things on the smooth manifold. Okay, so the usual way when your manifold is smooth is to put a Riemannian metric, G. So it's simply a smoothly varying collection of inner products over the tangent spaces of my manifold. And by setting a Riemannian metric, it induces distance on the space itself. So even though we are measuring things on the tangent spaces, we can actually define a notion of length simply by integrating the metric tensor over the tangent vectors. And it also defined by taking the infimum of the length of the curves that are joining 2 points. It defined a distance that is called a geodesic distance, which is a distance on the point of my on my manifolds and not on the tangent space. So all of this is induced by the Riemannian metric. All right. We don't see all the screen. Okay. I think it's okay. So, given a Riemannian metric, the simplest operation I want to perform is computing geodesic associated to that Riemannian metric. All right. So a geodesic is simply a locally energy minimizing curve, and it turns out by minimizing the energy, it also minimizes arc length. All right. So there are different frameworks for that, and the framework that I'm going to use is the framework of principal bundles. Okay, so let M be a smooth manifold, okay, and let J be a Lie group that is acting on M in a smoothly, properly, and freely way on my manifolds. Okay, then the canonical projection, so it's simply the quotient map that to a point associated its equivalence class. It defines a principal bundle on the fibers, defines the principal bundles whose fibers are simply the orbits of the element of my manifold under the group actions, right? So by defining a principal bundle, I can look at the tangent bundle of my manifold, and I can always define a notion of a vertical bundle. So the vertical bundle is simply the kernel of my quotient map, of my submersion, right? And now, if I endow my manifold a Riemannian metric G, it also canonically defines a way of an horizontal bundle taken as the orthogonal complement with respect to that Riemannian metric. So we are looking for two conditions. We are looking for group action on my manifold such that the action is isometrically with respect to the metric. And we're also looking at the fact that we want to split the tangent bundle, so the set of all the tangent spaces. We want to split each tangent space into a vertical part and an horizontal part. Okay. Now, if I undo my manifold a Riemannian metric, it gives me a canonical way of splitting into a vertical part and an horizontal part. Okay, so it gives me a distribution of horizontal spaces that is equivalent, and this is simply called in Riemannian geometry a principal connection. Okay, so now I want to perform computation on my quotient space. Remember, my goal is to compute the geodesics on my quotient space. So the usual way to do this, given a distribution of horizontal subspace, is to lift the computation into the top spaces. and we want to lift them at the horizontal subspace. So for that, we define a notion of horizontal lift of a vector field. So if I have a vector field on my quotient space, which is my bottom space, I can lift it to an horizontal vector field in my top space, okay, which is horizontal and which projects via the quotient map. All right. So this definition, it gives a hint of what is a tangent vector in my quotient space. Well, a quotient tangent vector, so I name it a quotient tangent vector in my quotient space, is simply a G equivariance and horizontal vector field along the fiber. So if I have my point in my quotient space here, phi of P, I can look at the fiber above that point, which is simply the orbit of P under my group action. Okay. And this tangent vector here, it can be identified with this blue vector field, which is horizontal and which projects to this tangent vector. Okay. So if I have a right action of my Lie group on my manifold, okay, my horizontal distribution is smooth, and it is also equivariance. Okay, so if I want to go from here to here, I simply let the group act on the fibers. Okay, so let's go back to SPD matrices, covariance matrices. Okay, so we have a very similar construction. We have the group of orthogonal matrices that is acting on the space of general linear matrices in a smoothly, freely, and properly way, simply by right multiplication. Okay. Now the Frobenius metric, so the usual metric on matrix space, Euclidean metric on matrix space, turns this group action into an isometry and the quotient map into a Riemannian submersion. Riemannian submersion is really this condition. RG is an isometry. Okay, so if I consider a symmetric section of this bundle, because I want to measure things along the quotient space, but one method to do it is to measure things along a section of that space. So I'm going to horizontally lift my computation specifically along that section, and then I'm going to use the equivariance along the fibers to say, okay, I can if I know how to lift it, my computation along the section, I can actually lift it everywhere in the top space simply by letting the group act. So I take a symmetric section of this bundle, okay? So W equal XX transpose, okay? And I have also a diffeomorphism from S plus 2 itself, okay, simply by taking the square roots of my matrices. So the inverse is simply the uniquely defined matrix square root for symmetric matrices. All right, and I have this commutative diagram. Okay. So commutative, it simply means that if I go this way or this way, it's the same thing. I end up here and it gives me the same computation. Okay, so I want to measure things into that quotient space. So my idea is to measure it along a section. Okay, so the symmetric section of SPD matrices. And turns out that this section is simply the symmetric positive definite part of the polar decomposition. Okay, so how do I compute the horizontal lift? Well, first I compute the Fréchet derivative of my quotient map, okay, along that section, so S over pi. It can be expressed in terms of a solution of a Sylvester equation. And if I inverse that Sylvester equation, I can get an expression of the horizontal lift along that section. And by making the group act, I can get the horizontal lift at any point of the fibers in my top space. Okay, so why all this horizontal lift? It's simply because in the framework of a Riemannian submersion, the geodesics below are simply the projection of the horizontal geodesics above. So if I start with a tangent vector below, I horizontally lift it, then I compute the geodesics in the top space, okay? And then I project back that geodesics to my quotient space. And if a geodesic starts with the initial horizontal tangent vector, it remains horizontal all the time. Okay, so how does it translate to correlation matrices? So we have this structure that we apply to SPD matrices. It gives us a metric on that space, okay, on that section, not here. But we can pull back it or push forward it by a diffeomorphism, and we get the the metric on that space. So if instead of taking GLN, we take a product of spheres of rank n minus 1, of rank n, but all the spheres are rank n minus 1. Okay, I precisely, in a very similar fashion, I get exactly the space of correlation matrices at the end. So I compute my geodesics here in my quotient space, and I push forward them using 2D diffeomorphism on the space of correlation matrices, and it gives me a metric that has a positive sectional curvature on the space of correlation matrices. And the metric on the top space is again the Frobenius metric. All right, so I have a bunch of metric on some spaces. I can do geodesic triangles, for instance, on full-rank correlation matrices. So if I take the usual affine invariant metric on the space of SPD matrices and using the quotient thing, I make it descend into the quotient affine metric on correlation matrices. I can see that I have, using the geodesic triangle, I can see that my geodesic triangle are deflated, which means that the curvature has an hyperbolic behavior. Okay. Same for positive curvature. My geodesic triangle are a bit inflated, so gives you positive curvature. And I could also use, and this is what I'm gonna display in the last part, log Euclidean framework for correlation matrices. So I just have a diffeomorphism that kills the curvature and bring the correlation matrices to a space of, to a Euclidean vector space. And I compute the geodesics in the Euclidean vector space, and then I pull back my geodesics. So this is my weird Euclidean vector space, okay? I give it a Riemannian metric with a null curvature on it, and I pull back it by diffeomorphism, by a complicated diffeomorphism to the space of correlation matrices. It gives me a log Euclidean framework, okay, for having a Riemannian metric on the space of correlation matrices. Okay, so why correlation matrices in the end, and the link with functional neuroimaging. Okay, so correlation matrices are widely used to describe the brain connectivity in functional neuroimaging. In fact, the resting state functional MRI provides a stream of images. Now you can divide each of the images into some parcels. You can build the covariance matrix of that images associated to that images. So it computes the covariance between each of the region of your images. Okay, and now you rescale it, and it gives you this type of matrices. So put one on the diagonal. Each region of the brain is obviously perfectly correlated with itself. And we can slightly observe like some sub-diagonals here and here, which would translate as higher correlation between left and right hemisphere of the brain. All right, so if I use my log Euclidean framework for this stuff, I have this time series of functional connectivity of the brain of some subject. Okay, so this is a very high dimensional object, but I use a 3D PCA to see the trajectory of it. Okay, it gives me this curve that is clearly not smooth at all. Okay, now if I apply a diffeomorphism, I have this on it, and it translates into some weird Euclidean space. I have this weird phenomenon of completely smooth curves. And I use a PCA in 3D to visualize it. Okay, so now my idea is very simple. Rather than making a polynomial interpolation onto this trajectory, I'm going to do it also on this trajectory. It seems more smooth. But keep in mind that those are very high dimensional objects that we project in 3 dimensions. So I cannot say much thing about it. Okay, so we can perform a polynomial interpolation on the base signal. Okay, but we of course also perform a polynomial interpolation on the signal obtained by applying a diffeomorphism. And after performing the polynomial interpolation, we use a PCA in 3D just to visualize it, right? Okay, now that I've done this, I can take my polynomial interpolation in my weird Euclidean space and transport it back using the inverse of the diffeomorphism in my original space. So both of these curves, they live exactly in the same space. So in dark blue, I have the original signal, right? And in light blue, I have the interpolated signal. Okay. Now the big question is, what is the difference between the original polynomial interpolation and the polynomial interpolation we obtained using the Euclidean framework? And the big thing is about interpretability. So the signal, they really look alike. They are really very close to be the same. In fact, we minimize the same loss by doing the polynomial interpolation, which is just the mean square error. Okay, but the big difference is all of the blue points here, the light blue points here, are in fact correlation matrices, while all of the blue points here are not, because the polynomial interpolation onto the space of correlation matrices, the original space, if you take a operation on correlation matrices, it will end up in the space of symmetric matrices, but it will not remain SPD. While if you do it on the space I showed you before, it remains SPD. And you have a correlation, you have a signal where each of the points, so each of the points of your polynomial that approximate your original signal is now interpretable as a matrix that represents the functional connectivity of some brain. So this is a time series of correlation matrices, and this is not, even though the signals really look alike. So we have a bunch of Riemannian metric that are all implemented in the Python package geomstats. And I think I'll leave you on that slide for this talk.